Okay, so putting a giant data center in space, that sounds like something straight out of a sci fi movie, right? But what if I told you that some of the biggest names in tech, we're talking Elon Musk, NVIDIA's Jensen Huang, they're actually talking about this for real? So let's get into why. And this quote, it just nails it. This whole idea is sitting on a razor's edge. It's either completely insane, one of the worst ideas ever, or it's just where we're headed next. There's really no in between here.
And look, this isn't just a couple of billionaires dreaming. We're talking about the big guys. Google, Amazon, they're all sniffing around this idea. And that tells you something, right? There has to be a huge problem on the ground that's forcing them to look up. So what is it? What's the problem that makes launching a supercomputer the size of a city into space seem like a reasonable solution?
Well, the crazy thing is, the push for space isn't really about space at all. It's about a problem right here, at home. The bottom line is, we're kind of running out of Earth. So here's the deal. This whole AI explosion, it's just incredibly hungry. It needs a staggering amount of everything. We're talking about building supercomputers as big as cities. Each one needs its own dedicated power plant just to turn the lights on. They suck up insane amounts of water for cooling. And trying to get the land and the permits to build these things on Earth, it takes years. And here's the kicker. The demand for this kind of computing is set to grow 100 times by 2030. You can see how this just doesn't work long term. Which, of course, brings us to Plan A, the big idea. If we're running out of room on the ground, why not just put the cloud, literally in the clouds? Let's build these data centers in orbit. And when you first hear it, it sounds so elegant, right? So simple. Down here on Earth, you're fighting for land, you're limited by the power grid, you're buried in permits. But up there, you've got all the space in the universe, unlimited, free solar power, and absolutely no red tape. It almost sounds like a cheat code. A little too perfect, maybe. And yeah, of course it is. This is the exact moment where that beautiful, simple dream runs face first into the brutal, unforgiving reality of physics. And trust me, it's a brick wall. There are 4 huge, huge problems we have to solve. Okay, so let's walk through them. First, you've got the computers themselves and how they even survive up there. Then there's power generation. After that, cooling, which is a bigger deal than you think. And finally, the small matter of getting all that data back down to Earth and keeping the whole thing from breaking. Okay, problem number 1, radiation. Space isn't this clean, empty vacuum. It's actually a shooting gallery of high-energy particles. And for computer chips, that's just a nightmare. These particles come screaming in, they flip bits in memory, they mess up calculations, they literally wear down the hardware over time. So you can't just toss a regular off-the-shelf GPU up there. It has to be rad-hardened or wrapped in a ton of shielding just to have a chance. All right, next up is power. And yeah, the sun is right there, totally free. But think about the scale we're talking about. To power just one kind of small 40-megawatt data center, you would need a solar array that's over 100,000 square meters. That's like dozens of football fields worth of solar panels. Just imagine that flying over your head at 17,000 miles an hour. It's just massive. And all that power, it generates a ton of heat, which brings us to what might be the weirdest, most counterintuitive problem of the whole thing. How on Earth, or I guess off Earth, do you cool a super hot computer in the cold of space? So this is where most people get it wrong. We all think space is cold, right? But a vacuum is pretty much the best thermos you could ever imagine. It's a perfect insulator. See, here on Earth, heat gets carried away by air or water. It's called convection. In space, there's nothing. No air, no water. The only way to get rid of heat is to radiate it away as light, like the glow from a hot piece of metal. And that process is incredibly painfully slow. So how slow are we talking? Well, to cool that same 40-megawatt data center, you'd need radiators with a surface area of around 120,000 square meters. That's another 15 or 20 football fields of stuff you have to launch. So suddenly your cool, futuristic space computer is actually mostly just a gigantic, clumsy radiator. And the price tag to get that radiator into orbit, it's just mind-blowing. Even if we use the absolute best-case, rock-bottom launch prices from SpaceX's Starship, which isn't even flying yet, you're looking at something like $400 million. And I gotta repeat this. That's not for the computers. That's not for the solar panels. That is just the shipping cost for the air conditioner. And okay, let's say you solve all of that. You still have 2 final killer problems: bandwidth and maintenance. First, you have to actually get the data from orbit back to Earth. You can use lasers, but our own atmosphere gets in the way and creates a huge bottleneck. And second, what happens when a part breaks? And parts always break. You can't just send out a tech with a screwdriver. Nope. The whole thing has to be built so you can just throw away broken modules and launch new ones. Which means, you guessed it, more launches, more mass, more money.
So, okay, low Earth orbit seems like a total non-starter, right? Too many problems, it seems like a dead end. But what if we're thinking too small? Some people are saying, forget orbit, let's just go all the way. Let's build it on the moon. A literal moonshot for our data.
Here's the problem with that idea, though. The moon doesn't actually solve any of the problems we just talked about. In fact, it makes pretty much every single one of them worse. Radiation? Way more extreme because you don't have Earth's magnetic field to protect you. Cooling? Still brutal, but now you've got this superfine abrasive moon dust that will get into everything. Power? The moon has 2-week-long nights, so you need batteries the size of a skyscraper just to survive till sunrise. And the launch cost? We're talking something like 20 times more expensive than just getting to orbit.
But honestly, all of that is nothing compared to the one single absolute deal breaker. And it's something no amount of engineering can ever fix: the speed of light. A signal from the moon takes 1.3 seconds to get to Earth. That means anytime you ask it a question, you have to wait 2.6 seconds for the answer. That round-trip delay, that latency, it makes it completely useless for almost anything we use AI for today. Game over.
Okay, so where does that leave us in this whole debate? We've seen that technically, from a pure physics standpoint, this stuff is possible. It's a ridiculously huge engineering project for sure, but it doesn't break any laws of science. But as it so often does, the real showstopper isn't physics, it's the money.
And when you're talking about data centers, it all boils down to one simple question, one metric that decides everything: watts per dollar. Basically, how much bang do you get for your buck? How much computing power can you buy for $1? That single number is what makes or breaks a project like this. So let's do the final math on our little orbital project. You've got roughly 400 tons of computers, another 400 tons for the solar panels, and 400 tons for the radiators. That's well over 1,000 tons you have to lift into space. With today's launch prices, you're looking at a $5 billion shipping fee. And remember, that's before you've bought a single chip. That's just the cost to mail the parts. So yeah, the verdict is pretty simple, isn't it? Right now, today, the math it doesn't add up. Not even close. The watts per dollar you get in space is just astronomically worse than what you can get right here on the ground. For now, it's just not a good deal. But I want to leave you with this final thought. We know launch costs are dropping fast. So what happens when they're 10 times cheaper than they are today? Or 100 times cheaper? Sure, we might still need a breakthrough in cooling technology or power efficiency, but it forces us to come back to that original question. Is this whole thing just pure madness, or is it somehow still inevitable?